Hello physics students, hope everybody's doing great. This is Mr. Kennedy again, and today I want to give you a little tutorial through something called Coulomb's law. Coulomb's law tells you the force between two charges. So let's start taking a look at some of the basics here. Coulomb's law. Now, one of the things that's really interesting about electricity is you can see the effects pretty clearly in your everyday life. So if I take just some normal Scotch tape here, take a piece of tape out, and I'm going to take this tape and I will basically cut it in half. Now what I'm going to do, I'm going to take the sticky side of one piece and the non-sticky side of the other, and I'm going to put them together, kind of like this. Chances are you did something like this in chemistry last year. And when I pull them apart quickly, you can see that when I bring them together, they attract each other. They attract each other because one of these strips became positively charged by losing electrons, and one became negatively charged by gaining electrons. And that's where we first see that opposite charges attract, and we actually see that like charges repel. So we don't see this in gravity very easily because gravity is a lot weaker. But we're going to see there's a lot of similarity between electricity and gravity right now. So with electricity, this is going to be with this force. This is the force that you feel electrically. This is a new force for us. And what it says is you have a charge, Q1. We denote charge by Q for some reason. We're running out of letters again. And charge Q2 here. And they're separated by some distance d. The force that you are going to feel is what is called Coulomb's law. The force that Q1 exerts on Q2, which is the same as that Q2 exerts on Q1 because of equal and opposite forces. The force that you're going to feel is K Q1 Q2 over, I'm going to make that d squared. There's d squared. Notice that this looks a whole lot like gravity. You've got what seems like a spherical kind of planet here, another spherical kind of planet here, and then you've got a distance here, and the equation is really similar to gravity, but the constant is very different. Constant is 9 times 10 to the 9th Newton meter squared per Coulomb squared. So this tells you the force between these two charges. Again, could be attractive if they are opposite, could be repulsive if they are the same charge, the same sign of the charge. But again, notice it still looks a lot like gravity. But the constant, again, is very, very different. Now, before we even get into that, these charges, this one and this one, are measured in a unit called coulombs. So these charges right here, these two charges, the units here are coulombs. And that's abbreviated with a capital letter C. But the problem here is that a coulomb is a very, very large unit. So you're not going to see that very often. You're going to see that a fraction of those coulombs, and I'll show you those right now. So because a coulomb is so large, as a matter of fact, lightning is on the order of magnitude of around 100 coulombs. So that's really, really large. Let's say we're going to use things a little differently. We're going to say we'll have the most common one is microcoulombs. That's 1 times 10 to the negative 6th coulombs. You'll have another version that you might see, nanocoulombs. That's 1 times 10 to the negative 9th coulombs. And then you'll also have picocoulombs, which is 1 times 10 to the negative 12th coulombs. And you can just put these in your calculator. Very similar to the way that we did gravity. When you did gravity, you had those big numbers that came up. Well, now with electricity, we have sort of small numbers that come up because the sizes of these charges are pretty small. Nanocoulomb is about the amount of charge that you would see maybe in a laboratory if we did something. Picocoulomb, that would about the piece of tape that we just pulled apart. We'd probably get about a picocoulomb on there. These are really, really small, but you can still see the effects of them pretty easily. But really quickly, let's do a quick comparison. If we looked a long time, we looked back, we saw gravity, the force of gravity was G M1, M2 over the distance squared, where G was 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. But for electricity, the force is K Q1 Q2 over the distance squared, where K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Almost said the same thing again. So notice that these numbers are very, very different. G, this gravitational constant, is times 10 to the negative 11th, where K is times 10 to the 9th. So a lot of people would say that electricity is much, much stronger than gravity. The only problem is that these two units are not the same. So you really can't compare these two things because a kilogram is not the same as a coulomb. But it certainly does look that you can see the effects of electricity much more easily than you can see the effects of gravity. So we're going to see those much more on a daily basis. We'll see the effects of electricity much more than we'll see the effects of gravity. So let's do a little sample problem. And once you know how to do one of the sample problems, then you can actually see that you could put these in a force diagram, you could put these in whatever else you need, because they're just another force. Just like you would have normal force or gravity or tension or any of these other things, you can put this in as one of the other forces. So let's take a quick look at it. Let's say we have, right here is a plus 3 microcoulomb charge. Remember, that's really times 10 to the negative 6th. And let's say right here we have a plus 2 microcoulomb charge. And we're going to separate them by 3 meters. So these two charges are going to repel each other. They're going to repel each other because this one's positive and this one's positive. When they both have the same sign, they'll repel. So they'll separate like that if we're going to let them go. But let's figure out how much force is actually going to be between them. The force between them, we start with K, Q1, Q2 over the distance squared. Okay, so if this is the force between them, now we just have to plug in all the information. K is always the same. Just like G was always the same, K is always the same. So K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. That one's done. Now this is 3 microcoulombs. The little mu symbol between that means micro. It means times 10 to the negative 6th. So this is 3 times 10 to the negative 6th coulombs. This is 2 times 10 to the negative 6th. 2 times 10 to the negative 6th coulombs right there. And then we divide by 3 meters squared. So this is going to give you the force between these two charges. So let's see if we can do this, and we'll see if we can actually do this whole thing in our head. So first of all, we see, you can just plug it in your calculator if you wanted to, but I've got 3 squared down here and I've got 9 up here, so that cancels. Then I have times 10 to the negative 6th times 10 to the negative 6th, that's times 10 to the negative 12th, but then there's times 10 to the 9th here, so that becomes times 10 to the negative 3rd, and then I've got 3 times 2 is 6, so this becomes 6 times 10 to the negative 3rd newtons. Now you could rewrite that if you wanted to just be 0.006 newtons. That's totally fine. But that's the force between them. The thing is, that's not a lot of force. That's not. these are decent enough charges, but they're 3 meters away, so you're not going to get that much force on them. But it's not zero. As these things get closer and closer and closer, you are going to see that the forces get larger and larger and larger. As a matter of fact, let's take a look at what happens with all these things as we keep changing it. So, what I recommend you do in these next type of problems is to let the equation be your guide. Let's say that I had a charge here, I'll call that Q, and I've got a charge here, I'll call big Q, and I'll separate them by a distance d. And let's just say that right now, the force between them is going to be 10 newtons. We say that there's a 10 Newton force between them. Now let's start changing some things and see what happens. And we'll see what the effects are. So we're going to use our equation. The equation is going to be our guide, but I'll leave some spaces in it. That's going to be Q and Q over the distance squared. So let's just say that in this first example, that what I'm going to do is I'm going to double the distance between them. Let's say I'm going to make this twice the distance. If I make it twice the distance between them, then what happens to the overall force? Well, I let the equation help us, but we can think about it. It's going to be less. The force definitely has to be less because they're going to be further away. So I bring this down, I put a 2 here, and what I see that now this is the equivalent of 1/4 in the denominator. You know, this is going to be, because this doesn't change, this becomes 2 squared, so that's 1/4. So now the new force is 1/4 of 10, so it's 2.5. That's going to be the new force between them. It's less. It's 1/4 less. The distance doubled, but because we have that square down there, it's going to be less. What if we instead tripled it? What if instead we tripled the distance between these two charges? Well, we triple it. Now we put a 3 down here. Now we can see that these don't change. So now this is going to be 1/9 of the original. Well, that means, if you do a little math on this, that the force between them is 1.11 newtons. It's 1/9 of the force. So if you let the equation be your guide, it makes these problems very similar to what we did back with gravity. Well, what if we made some other changes? What if I said, that I doubled this charge? I doubled that charge. Kept everything else the same, back to where it was 10 newtons, and I doubled that charge. Well, if I double that charge, you see the overall effect on the equation is to make it 2 times bigger. So then the force would be 20 newtons. What if I went and doubled both charges? I doubled this one and this one. Well, now there's a factor of 4. 2 times 2 is 4 there. It's just be 4 times bigger. And the force would be 40 newtons. Now you can keep going with this. Whatever combination you'd like. Maybe that I do something like this. I would say, maybe I double this one, triple this one, and make this 4 times as big. Well, what happens? I get twice the charge here. I get 3 times the charge here, and I have 4, but don't forget to square it here, times the distance. So this becomes, in this case, we get 6 over 16, or that's 3/8 of the original force. So that would tell me that this new force is 3.75. 3.75 newtons. So again, you can just base this off of the equation and you'll get some really good results out of it. So what this is actually us calculating the force that any electrical charges feel with each other. So for instance, if you were to take 2 things out of the dryer and they attract each other, that's the force you're actually calculating. If you were to, like I said, with the pieces of tape or anything else that becomes charged, That's the force that you're calculating here with Coulomb's law. So now you're ready to go ahead and try some of the problems on the worksheet. Feel free to ask me any questions. Feel free to email me if you want to have a quick phone call or a Zoom meeting. Just let me know. But hope everybody's doing great, and I can't wait to hear from you.